Hey folks, it is Dr. Powers here. We're going to go through the labs for Module 6. And I'm going to just kind of walk through the steps so you can get a sense of how you want to use stat powers to produce the kind of outputs that you're going for this. So we're concerned with comparing, looking at proportions still. We're looking at categorical variables for some like situations where it's more than just a single population and a single like two-level categorical variable. So we're looking either at comparing two different populations, or looking at two different categorical variables and seeing if they're independent between, like if there's an independence between the variables within a population, or looking at a variable that has more than two categorical levels and looking at goodness of fit tests. So we'll explore all of these in this video. The first one is this CPR data. And for this one, you want to go to the data analysis kind of part of stat powers, where you can pull up data sets. And the data set's just called CPR. So you can type in CPR and pull that up. You have to click load, and it'll pull up the data set. What you have here are two variables, group and outcome. And so it's really whether or not a blood thinner was given to the individual, and then it's whether they survived at least 24 hours. So what we want to do for this analysis is just we want to look at both variables. So click them both and click on contingency table, and it'll pull up a two-way table summarizing the observations. And so you can see, it'll tell you 11 individuals were in the control group and survived. 39 were in the control group and died, right? And so you can see how that's laid out. Now, what we're going to be doing here is we want to create a 90% confidence interval for the difference of proportions between the two groups. So what we want actually is we want to have the, so what we're going to do is, one thing about the contingency table is the groups are colored by row. And so if you notice, if you wanted to have the row variable to be the outcome rather than the grouping, you can transpose the data, and that swaps the direction of the table. Now we're going to be, we're interested in is the survival rate between the two groups. And if you're looking at the inference, I'm going to actually maximize this inference for proportion difference. What we're going to see here is here it's testing rows, and so what we're actually looking at is whether here it's actually looking at whether the proportion in the control group is different between the two, between those who survived and those who died. That's actually not what we want. So we actually want to transpose it, and we want to see whether we're checking the survived proportion for the two groups, and the groups are the control group and the treatment group. So the null hypothesis is that the proportion for the control group minus the proportion for the treatment group is equal to 0, meaning that they have the same. And the alternative is that they're not equal. So actually, I want to just look back at the lab. Yeah, so you can see just setting that up and doing the transpose, being sure you're picking the right row to test. Then you can see down below a confidence interval is calculated, and it's a confidence interval using the Wald approximation. Basically, that if you have a large enough sample size, you can use a normal distribution to approximate the distribution of proportion, sample proportions. At any rate, yeah, you'll see that your approximate confidence interval for the difference of proportions shows up right down there, which is to say, and you'll have the same kind of numbers because this is the same for everybody. Anyway, but that's how you'll get that. I'm just going to go through rather quickly so you have a sense of what's really involved in the lab. For the mammogram lab, we're going to actually go, I'm going to actually close this. I don't need this anymore, and I'm actually open up a different data set altogether, and that's the mammogram data set. And so what we have here are, we're looking at two variables, right? We're looking at whether the women were given a traditional breast exam or whether they were given a mammogram. And then we see whether or not within 25 years they died of breast cancer. And so, again, we're going to be clicking on selecting both of these variables and opening up the contingency table. So this is a very small sample size. Oh, I'm sorry, it's loading up. It's a very large sample size. You can see that we have 500 individuals from the mammogram group who died. This is breast cancer death. And then a lot of them did not. Okay, so let's go to the question we want to ask. We want to here do a hypothesis test to see if there's a significant difference. And again, we want to, oh, you know what? Let's see. Before we do this test, we want to, so in part of the lab, you're asked for the pooled proportion. There's actually a way from the contingency table to get the pooled proportion. If you look at the marginal frequency table, you get row and column totals, right? And if we look at proportions, that'll give us what proportion is in each row and in each column. So what this means is that now, ignore the table itself, but I'm looking at the column total. That's the breast cancer death rate for the entire sample, and that proportion is 0.01119, which is to say, out of the entire research pool, we had a 1.119% died of breast cancer within the 25 years. So if the two groups actually have the same proportion, that pooled proportion is our best estimate for a proportion, and that's used within the calculation for the hypothesis testing for whether there's a difference in proportion. So if we look down at the inference for proportion difference, and actually what we're checking again is we wanted to check. I'm going to have to transpose the data, and so I'm checking whether whether yes, meaning breast cancer death, is different between the proportion is different between the two groups. So the proportion for the mammogram group, the proportion for the control group. So when this is what's done in the calculation is a pooled proportion. And actually, you're not seeing it here, but that's why we wanted to just look at the pooled proportion. Anyway, this result is the same as the result that you would have from a chi-squared test. The p-value of 0.86978, you'll notice, is the same as the p-value here, because actually the two tests, although they use different methods, mathematically what's happening is the exact same thing. Anyway, that's all you have to do to pull that stuff up. Let's take a look at the next one. Actually, I'm going to skip over to Lab 6.4, which looks at a different type of test, which is the goodness of fit. So this uses the jury data set. I'm going to pull this up. All right, in this one, what we have is you have 275 individuals, and they've had their race is classified under Black, Hispanic, other, and white. So we have 4 categorical levels. And so what we want to see is whether or not the proportions within this data set matches a null distribution, which is the county demographics, and see whether or not they're representative of the county or whether there's something funny going on where people are not getting fair representation on juries based on race. And so the evidence would be that the proportions in the jury data are significantly different from the demographics for the county. So all you have to do is select that one variable and open one variable qualitative analysis. It's going to bring up the data, and we can you can actually get, you can look at your summary statistics for this data set. But what we're going to be doing is performing a goodness of fit test. It organizes these alphabetically. We can actually, if we wanted to order it a different way, we could. But what we're going to do is we're going to test whether the proportions are different from the null distribution. And those are given with 72% white. And I'm going to just put in 0.72. Other was 0.09. Hispanic 0.12, and black was 0.07. Those can be put in as proportions. They don't have to be in frequencies. They'll get scaled up so that you'll get expected frequencies when the test is performed. So that this is to say, if our sampling matched exactly these proportions, which are this null distribution, this is what we would expect to see in our sample data. We would expect to see 19.25, which of course you're not going to see a quarter of a person, but when we say expected, this is in the sense of a random variable, which is to say if you were to do this sampling 275 people over and over and over and over and over again, a long-term average you'd see would be 19.25 for this first group, and then 33 for the next group, and so on. That's what we mean by expected frequency. Anyway, the test is going to tell you whether the observed frequency is significantly different than the expected. And by significantly, we mean more rationally attributed to a true difference in the population rather than just the randomness of sampling. Let's take a look at the S&P 500 data set, because this one we're actually going to be doing getting streak analysis from the time series analysis. So the data set is SP 500 from 2009 to 2018. I'm going to load this up, and actually what we want to do for this one, we're going to be looking at the two variables open and close. These are telling on various dates whether what was the opening value of the S&P 500 and the closing at the end of the day. So we're creating a new variable that we're going to call change, and that is going to be close. If close minus open is greater than 0, we're going to say up, and we can say otherwise we'll say down. We don't actually have this last after the semicolon. A blank condition means always use this other label. So it'll be up, and if it's not up, it'll be down. The lab instructions don't actually say that. If you leave off the last part, it'll just call them, oh, you know what, I think I just need to, there. You don't want to have a blank space. Just have nothing, a semicolon, and then colon. Of course, I could explicitly say if close minus open is less than or equal to 0, and that'll do the same thing. But you don't even have to specify this alternative condition if it's just the complement. So anyway, we have ups and downs, and that's what we're looking at. We're looking at the change day to day, and we're going to be, rather than, actually we'll be looking at both, looking at this as a qualitative variable as well as in time series analysis. So I might as well just open both of them up and have them side by side, because we are going to be looking at both of those. In time series, we're going to be looking at the trends of ups and downs. How many up days in a row? So under the streak analysis, we've done this for other labs before, for the shooting baskets. We're looking for streaks up until and including up. So how many ups in a row? So what we have then, if you look, you have the first one is a streak of 1, and then we have oh, let me see. We have the first one, and then it goes down, then up, down, then up. Then we have down, down, then up. These are how many days until and including the last up. So we're going to be matching this up with a geometric random variable defined in the same way. So that's why we want to set it up this way. All right, if I click on this, I want to analyze these streak lengths as a qualitative variable rather than quantitative, and so I'm going to pull that up, and actually it opens up a new window. You can see my other stuff is still there. Although my data is numerical, I want to analyze it as a categorical variable because we're doing a goodness of fit test. And so actually what I'm going to do is I'm going to replace the 7s and the 8s with 7 plus, because for this goodness of fit test, we don't want to have any of these categories where we had too few observations. So I'm going to collapse 7s and 8s into a 7 and plus category. And you can see these are my, these are all the values that I have, and how many times they occur is given here. Okay, so what we need to do next is to build a null distribution. And to do that, what we need to do is to go back to we're going to just look at what the proportions of downs and ups are in the original data set. And that's what I opened up as qualitative. So I'm looking here, and I could see that the proportions for up is 54.338. All right. Similar to what we did with Kobe, we want to see whether the streak distributions are any different from what we'd expect if the S&P was just kind of independently going up or down every day and going up with just a 54% chance every day. All right, so this is going to be done under the we're going to be using this 54%, and I'm going to tuck this streak lengths over to the side. In fact, let's just minimize it so it's a little bit more out of the way. Sorry, it's a little bit finicky. Okay, you can actually open this in the same window now that I've added these little pop-up buttons. But what we're going to be doing is building a geometric, and I'm going to use the pop-up to have it in a little pop-up panel rather than a new tab, so we can do it all in one screen. All right, we're going to look at the probability of quote-unquote success to be 0.54338. That's the probability of going up. So we're looking at down streaks and the length of down streaks. And so what we are going to look at here is these probabilities that you have one down, or basically a streak of length 1, which is to say, like, that would be it's up in a row, up twice in a row. Like basically no downs before the first up. So I know it's a little bit confusing, but these are the numbers that you'd be using in this distribution. So what we have here are, from our streak length analysis, we've got the observed frequencies for your different streak lengths for 1, 2, 3, 4, 5, 6, and 7. And then over here we can calculate the expected probabilities, proportions for streak lengths of 1, of 2, 3, 4, 5, and 6. Now for 7, you don't just go to the probability of 7. What would be better, because we've collapsed 7s and 8s and anything above into one category, look at the probability above, and that's above and including 7, so 7 or more. That's the probability you're going to want to use. And then you can use in this streak lengths, going down to the goodness of fit test panel, you'd have to enter in the proportions that you have. Oh, I think since I renamed the thing, I don't think it's, it might have to just regenerate. It might have actually been there, and I just saw the number 8, and I thought that this was a category 8. But anyway, you might need to click this calculate now to regenerate the table. the inputs. So you put in your null proportions there for this null distribution, which is to say, if the S&P 500 price is just increasing or decreasing independently, this is the distribution of streak lengths we would expect to see, and we want to see whether or not it's significantly different. So that's how you'll perform that test. And I won't do the whole thing for you. I just want to leave it at that. All right. And let's see. I'm going to talk just a little bit about that discrimination at university, acceptance rates by gender. Now this one is similar to a lab we did early on. I'm going to open up the population generator over here. What we have is a hypothetical university, and we're going to be looking at the acceptance rates within each of these programs to see whether there is gender discrimination. And so what you want to do for each one of these is generate a sample of 500 from each program. So in fact, what you need to do is expand sampling options, because what we're going to be doing is not a simple random sample, but a stratified sample. So I pick stratified, add a stratum, and I'm going to say I want to have 500 samples from program A. And then that's when I want to generate my sample. And really all we're looking at is we're looking at the acceptance rates by gender. So the two variables I want to analyze are gender and accepted rate. And then I'm going to just click Analyze. What it's going to bring up for me in this pop-up is the same kind of thing we've seen before. What we can do then is, since we're really looking at the question of whether the acceptance rate is the same or different between the two genders, this is essentially, you can do this using a independence test. You can also do it using a proportion test, but I'm going to do an independence test because it's pretty fast. And you expand that, and you can see right there it gives you a chi-square value and a p-value, and the p-value is what you're going to be using. And then you can go back and do this for program B, and then resample, and then I'm going to analyze that, and we're going to do the same kind of thing and just continue and continue. It may possibly be that one of your sample size is so small that you violate that at least 5 under at least 10 in each of the cells of your table kind of rule, in which case don't worry about it. Just continue the analysis. It's not a big deal. So anyway, and then at the end of this, you're asked to do a little bit of thinking about family-wise type 1 error rate. And the question really is to say, like, if actually you might have done this, you'll compare this for group program A, B, C, D, E, and F. That's 6 different hypothesis tests you're going to be carrying out. And you want to just suppose that the null hypothesis is actually true in all 6 cases. That means each case you have whatever your significance level is, say it's 5%, you would have a 5% chance of getting a p-value so low you'd reject it, right? Make a type 1 error. And so the question is, what p-value would be better? So what you're going to be doing is opening up a binomial distribution, and I'm going to do it in the pop-up so we don't lose anything. And since we're doing 6 tests, you want to put the trials to 6. And we want to set the probability of success, and that's the probability of a type 1 error in this case, to 5%. And the question is, what's the probability that we would get 1 or more rejections if, in fact, all the null hypothesis was true all the time? And you can see, if you're running 6 hypothesis tests, the probability that at least one of them gives you a reject when your significance level is 5% comes out to be 26.49. So you can actually go to, okay, let's bring the significance level down to 0.04. Okay, now my family-wise kind of type 1 error rate would be 21%, which is to say that you have a 21 or 22% chance of getting at least one significant, p-value, even though in fact, none of the null hypotheses are false. All right, so what the idea is, you want to adjust this probability of success, which is essentially the significance level. Figure out what significance level would bring the family-wise type 1 error rate down to 5%. You can play with that, and you'll see when it gets there. All right. That's it. I know this isn't a full tutorial and everything, but hopefully this is going to help you see what you need to do to run these labs. And I hope they go well, and I hope you get something from it and get some good experience. All right, I'll talk to you later. Bye.